Yeah, start again. Got it. So yeah, let's connect and we can provide you with the access and help you with onboarding as well. And then what the best thing you can do is provide us with the feedback so that we know that it's working for you guys or not. Because at this point it's really crucial because we have a lot of things to build. It would be great to build the right thing. Exactly. What example maybe developer something. That's what we've been lacking right now.
Hello everyone. I will be speaking about the CTF that was prepared by Decurity. This is the company that I'm working for. This is a security company, and we did a CTF for ETH Dubai event. Has anybody of sitting here actually tried any tasks in CTF? Okay. So I will be then explaining the vulnerabilities of each task and try to explain more about the root cause of each vulnerability. Okay, there were 6 tasks overall, ranging from easy ones to hard ones. First one is WCoin. This is the easiest one. This is the snippet of vulnerable code. This is really a simple bug. WCoin is just a simple ERC20 token, and which is ownable one, means that it can be owned by somebody. And in ownable contracts, of course, there is a function to transfer ownership to some other address. And normally, this function, transfer ownership, should be protected, of course, so that only current owner can transfer ownership to some new address. And in this task, we just removed only owner modifier so that anybody could just transfer ownership to any address and become the administrator of this contract, and it effectively gained you a flag. This was the easiest task in the CTF. So more players are coming, which is good. So I will move to the second task, which is, I guess, more complicated one. This task was called X token, also under ERC category, meaning that it was just a token that had some functionality about the fees. So this token had some fee mechanics, earning some fee to on each transfer to the protocol. And there was a function to change the address to which fees are transferred, all the collected fees. And in order to call this function to change the fees recipient, the following function, check signatures, was used. If you look at it, you can see that there is a loop that iterates over signatures, and there is one important check that is missing, namely that this code does not check that the length of signatures array is not 0, is not empty. So this means that this loop will just not execute at all. And after that, we see another require is_admins, which contain the argument of which contains another array which contains the recovered addresses from the signatures. Of course, if we do not have any signatures, the admin's array will also be empty. And this code just will always return true if the size of the array is 0. So this is how exploit looks like for this task. We just initialize some empty arrays for signatures and just assign ourselves the address of the exploit as the fee collector address. And this call set units for fee collector will pass, so we become the fee owner, and after that we just make consecutively 15 calls or more. This is just random numbers that guarantees that we pass the check in isSolved function, which checks the state of the contract. So we make 15 transfers to the payer, and then we call the function scheme on this pair. The function scheme just withdraws any extra tokens from the pair. So it just checks the internal reserves and withdraws some extra balance. So as you see, we firstly transfer directly some tokens to the pair without calling add liquidity, if I'm not mistaken, in the units for pair, which is the correct way of adding liquidity into the pair. And we call scheme to get back our tokens, but the actual effect of this call will be that we will also collect fees, and the fees are ours because we just set ourselves as the fee collector. So effectively, after this loop, we get all the fees from the pair. So the next task is about a decentralized exchange. It's an exchange which operates an order book, unlike Uniswap, which uses AMM approach. This is an implementation for an order book decentralized exchange. So the vulnerability, I guess, is quite simple here, but there is some additional code that you should have investigated in order to understand how to solve this task. Well, the core issue is the line that is highlighted. This function by order market is used to fill some orders that were previously listed in this exchange. And the bug here is that in this require statement we check that balance of a user is greater than amount. And this is not correct because we should check the balance with buyer price, not amount. Which means that we can pass any amount. Well, not any amount, but some unexpected amount. Let's look at count balance. The count balance looks like this. So it just checks, it just returns the balance of the user. So it just looks at overall balances and subtracts log balances. And due to the bug with requires statement, it's possible for the log balances to be greater than overall balances, and it leads to integer underflow in this case. And we added a comment that this is so-called gas optimization using unchecked. But of course, this was done so that the underflow was possible, because in Solidity versions greater than 0.8, there is built-in protection against integer overflows and underflows. So we had to add this unchecked statement. So let's look at how it could be exploited. So in setup we had two orders, one large order and another small one. And in this setup, a player has a small balance so that he cannot fill the big order. So the sequence of actions from the player should include three steps. So firstly, we make our own order to sell 7 tokens. Then we fill this small order that was placed in setup, and at this stage we effectively gain integer underflow. So after that, our balance is enormously high. So all what we should do after that, just withdraw this balance and get the flag. Well, this is the most, I guess, unexpected task among all other ones, because other tasks were EVM-based, Solidity ones, and this was tagged under layer 1 category. For players, we prepared a special fork of Avalanche Network. This task is actually based on one of our audits. We were auditing an Avalanche fork, so we just tried to re-implement what we have seen at this audit. Well, basically, we added just one transaction called transfer transaction. It's important to say that in Avalanche there are several networks, P-chain, C-chain, and X-chain. C-chain is EVM-based chain, and this task was about P-chain. It's not something that you can find in Ethereum, so you had to dig into documentation to learn something about it. We didn't expect that you would just grasp all the details of Avalanche, and it was needed for this task, but I had to explain the core reason for the vulnerability to exist. Unlike Ethereum, Avalanche is a UTXO-based blockchain like Bitcoin. So I guess many of you know what UTXO is. It's an unspent transaction output. It differs from standard account model in Ethereum in that way that when you make a transfer, you spend some input and produce an output, and one account may possess different outputs, and the sum of amounts in all of that outputs is the actual balance of an account. And each output is signed by a private key of the owner of this output. So one important check when you are dealing with UTXOs is that you check that they are actually signed by the addresses that are specified in unspent transaction outputs. In Avalanche, this is the field output owners. And if you look at Avalanche transactions in pchain, in platform chain, you will see most of these checks. Well, you will see all of these checks actually. So this is just sanity checks that you are not trying to double spend, you are not trying to spend the balance of some other account, and so on. And in the transaction that we added, we just removed the check that tries to recover the address of the signer of the transaction inputs. So it means that you could basically spend the balance of any account in this network. So it's pretty simple. And we added a special endpoint, previous spend, that could basically prepare for you any transaction spending some other account's balance. So what you should do, just previous spend from pre-funded addresses and execute this transaction, which will transfer funds to you, and that was the that was checked by our checker script. So we just check that you have a positive balance in our system. So yeah, I hope that I explained it. Well, the next task is also based on one of our audits. Namely, it was the critical vulnerability that we found in the 1-inch smart contract. By the way, the audits were released today. You can find some interesting findings. So this was one of the vulnerabilities, critical ones in 1-inch contracts. So the core reason of this vulnerability is that there was a before token transfer hook in ERC20 contract. Before token transfer hook is a standard one. You can find it in Open Zeppelin contracts, which is executed before any transfer, as the name implies, of course. And in this hook, people usually add some actions that they would like to do before transfers for additional accounting or something special. In case of 1-inch, there was some also special accounting. And in this case, there is a function called set balance accounting, which allows you, well, anyone to set an external contract associated with your address. So it means that this external contract could be called on any transfer that you make just before the balances are updated inside ERC20 token. And each may be critical when you do some accounting before actual update, which means that in this task that we could just make another deposit, because as you see, it reads the current balance before this transfer was made. So the flow is that we firstly set our malicious contract as balance accounting contract. Then we make a deposit. Well, we make a transfer first, yeah, then our contract gets called, then we call deposit. At this moment, we call deposit from our malicious contract. And at this moment, the balance of in the requirement statement will return 0 because the internal state is not yet updated, and it allows us to deposit more and mint more than was expected. So we could just make extra deposits from callbacks, from re-entrancy actually, from our contract. And the last task was called My Token. It was about upgradability. Unfortunately, we had a bug in production, as I mentioned in the chat. So the root cause of the vulnerability here is that we allowed anyone to initialize the implementation contract, which is critical when it's a UUPS proxy implementation. UUPS means that the logic which upgrades the contract lies in the implementation itself instead of the proxy. So we could effectively initialize the implementation, then call upgrade to and call function with our new implementation, and just call any function on our token, on our contract of our choice. Well, in most cases, this is actually okay unless this new implementation does not self-destruct. And of course, in this task, we required players to upgrade this proxy to an implementation that would self-destruct itself. What it means? It means that the proxy will lose its ability to upgrade itself in the future. Because as I said, in UUPS proxies, the implementation is responsible for upgrading, not the proxy contract. So if we just kill the implementation, the current implementation, the proxy is just bricked. So the flow is simple. We just need to initialize the implementation contract, just directly call initialize on implementation contract, and create this new implementation which just self-destructs itself in some function, for example, in function kill, and call upgrade and call functions so that we set our malicious implementation and pass the function selector of function kill in the data argument. Sorry guys for the bug, we fixed it. I mean the checker script, checker function, because we forgot to update its implementation on production. So thank you for understanding. Yeah, this is how the malicious contract that kills itself looks like. So it just, as I explained, the extra function is proximal UUID, which is required by UUPS proxies. It just returns the implementation slot address. This is the results. The first place goes to .wader. I'm not sure if .wader is here. Oh, nice. Okay. Congratulations. Please wait is also here, I guess. Yeah. Please clap to the second place. And third place, GNU. No? Here? Ah, okay. So everybody's here. This is nice. So guys, I will give you some prizes. after this talk. And there's a guy from San Francisco with nickname Yakuhito who was the first actual one to solve all the tasks except the final one, but this was our mistake, so we will also sort it out. I mean, some prizes for Yakuhito. Thank you to him as well. Okay guys, thank you for your attention. I hope this CTF was fun for you, and until next time. Great question. It's ETH Dubai dash CTF.decurity.io. It's this one. Yeah, I think it's lack of communication. But in our socials, we try to push it on Twitter. Maybe each ETH device should also announce it more properly.
Is it will be available some next days?
Yes, I guess we will not shut down the servers for a while. So yeah, I guess you can try until next week maybe. Okay. Okay, I guess this is all. Thank you guys.